Sandipan, am I audible?
Yes, Shomita.
Okay. Good afternoon to all of you. On the behalf of the Department of Computer Science, and I heartily welcome all the participants here to this international webinar, Wonders of the Nanotech World, which is jointly organized by the Department of Computer Science and IQAC, Government General Degree College, Singur. I also welcome all the respected faculty members of Government General Degree College, Singur, as well as other colleges and universities, and the respected dignitaries present here. Dr. Choitali Chaudhary, the coordinator of IQAC and head of the Department History, Government General Degree College, Singur, is also present with us. I welcome Dr. Chaudhary in this virtual platform. Dr. Chaudhary constantly supports us to organize this international webinar. My gentle request to Dr. Chaudhary to say a few words. Dr. Chaudhary, please.
Am I audible?
Yes, yes.
Okay, thanks, Shomit. On behalf of IQAC, I welcome you all in this international webinar on Wonders of Nano World, organized by Department of Computer Science. Our today's speaker is Dr. Subhrangsu Sarkar, Postdoctoral Fellow, Department of Physics, University of Fribourg, Switzerland. A hearty welcome to you, sir. We might know the story of David and Goliath and how David, the young boy, defeated the hulking Goliath. The story proves that small is not synonymous to weak. We are aware that the nuclear devices, how a small particle can create immense energy and power through fusion and fission reactions. The story of David and Goliath coincides with today's topic, the wonders of nanotechnology, which involves the use of microscopic particles and is more useful than we can think of. From making fibers to curing cancer, it is truly a wonder. The uses of this wonderful technology will be explained by today's speaker. Thank you once again, sir, for being here, and thank you all.
Thank you, ma'am, for your valuable speech. Always you encourage us to organize such this webinar. Thank you, ma'am, once again. Nanotechnology is a branch of science and engineering that devoted to design, producing, and using structure, devices, and systems by manipulating atoms and molecules at nanoscale, that is, one or more dimensions of the order of 100 nanometers or less. The application of nanotechnology can be very beneficial and have the potential to make significant impact on society. Nanotechnology has already been embraced by industrial sectors such as the information and communication sector, but is also used in food technology, energy technology, as well as some medical products and medicines. Nanomaterials may also offer new opportunities for the reduction of environmental pollution. Now, I wholeheartedly welcome today's speaker, Dr. Subhrangsu Sarkar, and express my gratitude for accepting our invitation. Dr. Sarkar presently is a postdoctoral fellow in the Department of Physics at the University of Fribourg. Prior to this, he was a postdoctoral fellow at IISc Bangalore. He has obtained his PhD from KIFR Mumbai. His area of interest includes condensed matter physics, nanotechnology. He has more than 15 publications in international conferences and journals. Now it is the time to enter into the nano world through the lecture of Dr. Sarkar. I'm requesting Dr. Sarkar to deliver his lecture. Dr. Sarkar, please.
Good evening, everyone. Am I audible?
Yes, sir, you are audible.
Thank you for the kind introduction and giving me this opportunity. It's indeed a pleasure to be here to share a little bit of my work that I do and the immense opportunities that lie ahead. Now, without wasting more time, I will straight go into my talk and start presentation. As explained before, today's topic is a part of a lecture series, Wonders of the Nano World. And I will share with you a little bit of my experience and motivation that I had during my PhD and present research work. Since prehistoric times, humans have always been fascinated by big. About 4,600 years before, we created pyramids, which has a volume of about 2.5 million cubic meters. At the same time, we have unearthed world's largest diamond, which is Cullinan diamond, which gave birth to 105 smaller diamonds. We have an airplane today, a cargo plane, which can lift about 450,000 kilograms of mass. As you have already known, the Large Hadron Collider created a world record earlier by creating a tunnel for experiments of particle physics, which was 27 kilometers long. And now they're expanding that tunnel to 100 kilometers. In future, we'll make bigger and bolder structures, which is not only limited to physics or engineering, it's also limited to sports and other achievements. But at the same time, we ask the question, is bigger always better? And the answer to that is that sometimes, yes, bigger is better and we desire bigger. But our experience tells us that it is not always the case, especially when it comes to the computers and technology. On the left of the screen, we have Vannevar Bush's differential analyzer. This huge machine was built around 1930s, and it could do only 6 integrations at the time. And for doing these 6 integrations, they needed several people who had to agree to get practically drowned in oil to do these experiments. In the middle, this is the first transistor, which was developed by Bell Labs. And that transistor right now has been miniaturized in a level so that you can find more than 2 billion of them in your pocket every day. So when it comes to computers and technology, smaller is definitely better. And it brings us back to an old story of David and Goliath. Being a small boy, a tiny person, he was able to defeat Goliath. Nobody expected this to happen, but it happened because he was not only smaller, but he was different from the others. Same goes to Gulliver's Travels when miniaturized Lilliputians were able to pin down a huge Gulliver. So which brings us to the question to the material science, or the observation to the material science, which is relevant today. That smaller is not only powerful, but smaller is also different. It's different in a way that smaller gives birth to new science every day at this point of time. I am a material scientist who works in the branch of physics as well as material science. So I would like to tell you how we characterize a material of a known chemical composition. When we have something, we first ask the basic question, whether it's a solid, it's a liquid, or a gas. If it is a solid, which is of relevance of today's talk, then we ask, how hard is it? Let's say if we have a steel, or if we have aluminium, can we make a hammer out of it? And one of the response function is Ficker's hardness. Similarly, when we have a metal or an insulator, we ask about the electrical conductivity of that particular material, whether it is happy to let current pass through it, or whether it is absolutely resistant of any current flow. Whether it's a semiconductor, which has initial, which doesn't like the current to flow through it initially, but at some point of time, it agrees and current can flow through it, giving birth to new kind of devices and other stuff. Recently, we are also familiar with superconductors, which can allow current to flow through it without any resistance below a certain temperature. Similarly, we can also ask the question, what is the color of something? How does it react to light? And we call it optical property of that particular material. When it comes to magnets, on the other hand, we ask, if we have a particular kind of steel, what kind of magnetic behavior does it have? If it is ferromagnet, is it good enough to be used as a permanent magnet? Or is it better to use it as a transformer core, which is a soft magnet? Similarly, we ask, how does it react when we perform a reaction? How does it oxidize? And similarly, combining all these basic properties, we try to understand the other derivative properties, like what is the hydrophobicity, what is viscosity, granularity, etc. Beyond that, there is another way of characterizing complex systems or their properties. There are two different kind of properties that we every day encounter. One of them is called additive property, and the other is called emergent property. By additive property, we mean that if we add up the contribution of each individual component of a system, then we get the final property of that collection. Like in a ferromagnet, if we combine or add up the vector moments of all the spins in the system, we get to know the final magnetic moment, and then we can conclude how to use it and whether to use it or not. There is a different kind of property which we cannot understand by simply adding up the individual components. It's called an emergent property. Our brain, for an example, consists of millions and billions of neurons. And these neurons don't act alone. They talk to each other and they interact in a collective manner to generate a thought or a kind of consciousness that we are still going to understand in future. We have to yet understand in future. This property is called emergent property because it's not just dependent on one or individual representative units, but it's a complete interaction picture of everything that we have in the system. Which brings us to the central question of today's talk. How do these properties change when we reduce the dimension of these constituent elements? That is, make them smaller. Do they still behave the same way as they do when they're bigger? And how small are we talking about here? By small, we mean very, very small, in the scale of nanometers. For a common person or everyday person, it's difficult to understand the dimension of nanometers. It's smaller than we can think. We can try to understand it by using these two scales provided here. That one human hair has a width of about 50 to 100 micrometers. Micrometers means 1/1,000,000th of a meter. To give an example of how small nanometers really are, if every human were about the size of 1 nanometer, the whole world population would fit in a Hot Wheels car. That's a small toy car that you can buy in the stores. It's really that small. And for the rest of the talk today, we will confine our discussions to crystalline solids, especially nanocrystalline solids. In a crystalline solids, we have periodic arrangement of atoms. But in a nanocrystalline solids, we have this periodicity existing only in an intermediate range, but not in a long range. On the right of the screen here, I have tried to schematically explain what it means to have that intermediate periodicity. As you can see, this particle is made up of 3 different domains, and each domain has a different kind of orientation. So if we start walking from the red, one of these red balls here, after let's say about 5 or 6 of them, we will have to stop because there is no other space in that particular direction. So these intermediate periodic arrangements, or the length scales, are of interest to talk today. However, just like a bulk solid or a single crystalline material with an infinite periodicity or indefinite chain of atoms of similar behavior, it also has well-defined electronic and phonon bands. That means it has very specific electronic and phononic properties that are reminiscent of the bulk counterpart. A certain degree of these properties can be calculated by using computer simulations of well-established mathematical models, but the reproducibility and the operability of these models are fairly limited when it comes to these nanocrystalline solids. Now, how do we make them? How do we make these interesting structures? There are two different ways to go about it. Usually the people in the physics and engineering, they work in the left tree, in the vapor deposition technique. In a vapor deposition technique, we take a parent material, we make a physical vapor of it by either evaporating it or by making a plasma using an interaction between the electron beam, ion beam, or something like that. And then we drive that physical vapor of that material onto a surface of our own interest. This can also be done in a hybrid way, which is chemical vapor deposition. We take a parent material, like let's say gallium or something, or arsenic or something, and then we make a vapor of it, and then we drive that vapor onto another substrate, which actually reacts with the parent material as far as the chemical reactions govern. And because of this reaction, on the top of the surface, we have a new material which we didn't heat up before. So in the physical vapor deposition, we basically end up with the same material that we originally evaporated. Whereas in chemical vapor deposition, it's a new material that forms out of the reaction. The chemists, on the other hand, they go about it in a very different way. They do chemical reactions to create parent materials. One of it would be chemical root synthesis, in which you start growing them or making a reaction, let's say, which will create some gold or silver, and then you catch them young. What I mean by is that you don't let this parent material grow bigger than you want them to grow. And you can do it by using something called surfactants, which have a hydrophobic tail and a hydrophilic tail, and that will get attached to this material and stop growing. And the material would stop growing. So this is the most commonly used techniques for, let's say, growing gold, silver, platinum, or these kind of inert elements. On the other hand, there are a few different branches which has come up. One is Sol-Gel reaction, where you actually heat up already preformed bulk material, which then breaks down into nanocrystalline or nanometric sizes. Then there are hydrothermal synthesis, in which you basically perform a reaction in a controlled pressure and temperature range in a liquid environment, starting with a bulk solid. Under right conditions, that bulk solid will undergo this reaction and will give it will give rise to something which is really small, tiny, and we'll see an example of it later. Electrochemistry has been there in this planet for times even before we know about it. We gold plate ornaments, electrical panels, and everything using electrochemistry. But if electrochemistry is done carefully through different filters and other stuff, we can also end up with really controllable fine structures with a particular direction of growth. Whatever I told before is commonly phrased as bottom-up approach. And yes, in bottom-up approach, there is one small problem. Once these small particles are formed, it is not always possible to control their self-assembly or how they organize with themselves to get the final product that we want. Let's say we want something to be organized as a duodecagon. Can we really do it? It completely depends on the material that is under the question and how it reacts to the temperature, to the liquid, and etc. So it's sometimes difficult to control the self-assembly to get the final product. And for that matter, in electronics industries, for an example, people use a very different kind of approach, which is called top-bottom approach. In this approach, we make a big structure. Let's say we deposit a thick layer of gold, and then we break it down as we need. So it depends on what kind of interaction we are talking about here. For an example, in electron beam lithography, or any photonic lithography, let's say, we coat a substrate with a resist, then deposit the gold on top of it, and then by using an electron beam or light beam, we break down certain parts of the resist carefully, then wash it, and whatever is left is a nanostructured material or nanodimensional material. As discussed before, this is the most used technique in microprocessors, chip manufacturing, etc. Unlike the bottom-up approach, it has a plus point that we really know what we are doing and we can sort of control this thing. This is why these days, the microprocessors, the motherboards, they're so accurate because we exactly know what we are doing and we can do it. The limitation of this technique would be that it's still very expensive to do it. In fact, it's so expensive that right now in India, there is no state-of-art fabrication lab anywhere, not even in private sector, government sector, anywhere. We are completely dependent on countries like Taiwan or others who provide us with these parts. And then there is another issue. In this technique, the lowest element size that we end up with is not necessarily as small as a bottom-up approach. In a bottom-up approach, we can really end up with 1 nanometer or 2 nanometer of particle size. But in this technique, as you all know, I mean, it took Intel years and years to go down to 7 nanometer thickness in a FET. And 1 or 2 nanometer is still a dream, which I don't think it will be achieved very soon. Now that we have learned a bit about how we make them, let's discuss how we see them. The way to see anything is to use a probe of a particular dimension that is compatible with the size of that element. For an example, we can use light to see stuff which are about micron size or bigger. In a nanocrystalline material, the size of the element is of nanometers order. So we definitely need a probe which has a dimension of a nanometer or smaller. So technically, what we use, if I say technically correct, we use a probe of atomic dimension or smaller. Now we all know that an atom has a dimension of approximately 1 angstrom or so, which is even 10 times smaller than standard nanoparticles, order of magnitude speaking. And for this particular matter, electron microscopes were developed. An electron microscope works in a combined physical principle of wave-particle duality, or Heisenberg uncertainty principle, as well as relativity. As we know from quantum mechanics, wave-particle duality tells us that electrons, or ions for that matter, they are not exactly particles. They are either waves or particles, depending on the kind of experiments that we can perform. On the first picture that I have shown here, it's a scanning electron microscope, the setup that we have in TIFR or some other institutes like IISc. Here we use a field emission gun to create an electron beam, which has a typical dimension of, let's say, a few hundred picometers. And the dimension of single element of the beam is governed by the theory of relativity. So if we apply the laws of relativity, the energy of the electron beam changes also the wavelength as well as the internal structure of the beam. And using these two principles, we end up with a sub-angstrom structure of the probe beam. On the right-hand side, at the extreme right of the slide here, I have shown a TEM that is there in TIFR. It's Titan, FEI, Titan Transmission Electron Microscope. Unlike the scanning electron microscope, it uses a much more energetic electron beam of about 300 kilovolts, and it can go down to sizes as small as one single atom. In this picture in the middle, I have produced one scanning electron micrograph that I took for one of my samples. And using a scanning electron microscope, which uses an electron beam of, let's say, the energy of about maximum 30 kilovolts, we can go down to 2 to 10 nanometer easily. Not easily, but we can go down there. I mean, people do it routinely. On the other hand, if you use a 300 kilovolt Titan electron microscope, you can literally see the atomic columns. This picture on the rightmost side of the slide, on the bottom, is the picture of a nanograin, which has typical dimension of 5 nanometers. And you can easily identify each atomic column in that figure for that particle. And also, if you look carefully, you will see that this nanograin is not one single particle. It's actually comprising of more than one particles. This is the amount of power or resolution today's electron microscopes can provide you. Then there are two other direct observation probes. One, again, we are using atomic dimension of smaller, and both of them use atomically sharp tips. The instrument on the top is called atomic force microscope, which uses a cantilever, and the tip of the cantilever is atomically sharp, and it oscillates when it touches a sample, following standard laws of cohesion between two solids. And by monitoring the oscillation or the movement of a cantilever when it touches the surface, one can understand what kind of structure the surface has. Right now, it's so accurate that you can measure the thickness of one single atomic layer of graphene. The instrument below in the picture is a schematic of a scanning tunneling microscope. It's in IBM lab right now. And in this scanning tunneling microscope, unlike a cantilever, we use a very fixed, rigid tip, although atomically sharp, and this tip scans over the surface. Now, when it scans over the surface, there is a current that is passed through the tip to the sample. And by measuring how much current we are passing, or how much force the tip is, how much electrostatic force the tip is experiencing, we can understand the structure of the material, as well as a little bit about the composition. The atomic force microscope works on the principle of classical spring motion of a cantilever, whereas this scanning tunneling microscope, on the other hand, works on the principle of quantum statistical mechanics. At about 1990s, I think, if I remember correctly, now it is even possible to move one single atom, pick it up from the surface, and then place it on another place where you want to place it. It's not as easy as you speak, of course, but you can do it if you have enough patience to do this. This has brought us to a new era of nano engineering, or material science engineering in general, where we can create materials which have never existed in nature and which may not be supposed to exist. Now that we have talked about direct observation, let's understand how else do we do this. Not all of us will be rich enough to have an electron microscope, or let's say an STM or a TEM or an AFM. There are a bit cheaper options to do this. One would be to use X-ray diffraction technique. Similar to electron beams or atomically sharp tips, the wavelength of the X-ray can be manipulated by changing the target through which we generate the X-ray. Now, these X-rays have a wavelength which is comparable to the interplanar spacing, which is the most fundamental structure of a crystalline solid. As explained in, or as shown in the figure on the right, if we reduce the particle size below a certain dimension, these peaks that are generated because of constructive interference, they get broadened. So what we do in an X-ray diffraction is basically nothing but performing a constructive interference from atomic planes that are consecutively arranged. As we reduce the number of layers that are available for interference, the quality of the interference fringe goes down, and that gives rise to the broadening of these X-ray reflection or diffraction peaks. Now, there exists algorithms using which we can accurately characterize the size of a crystalline domain in a sample down to about 1 or 2 nanometer accuracy. Instead of using X-ray diffraction, similarly, one can use optical beam diffraction or electron beam diffraction as well. In the left of the slide, I have presented a selected area electron diffraction pattern of silver nanoparticles. The presence of multiple rings in the structure is an indication that the system must be nanocrystalline. If you want to know even further, I mean, it's a complete topic of a completely different lecture altogether. Basics apart, now I will tell you a bit about why are nanomaterials so special. Why do we care about it at all? Because of their size, the nanomaterials are neither isolated atoms or molecules, nor their bulk solids. They lie somewhere in the middle region of these two. To begin with, I'll show you one very familiar diagram of the vapor spectroscopy of hydrogen, sodium, helium, neon, and mercury. In a vapor phase, the state of the materials are more or less atomic. And as you can see, that as far as the wavelengths are concerned, there are distinct different energies or wavelengths that the spectra is allowed to have. The rest is black. Like, let's say in the blue square, we have represented 2 sodium D lines. And if you notice carefully, there is nothing on the left, nothing on the right. So the electrons are supposed to have an energy which corresponds to these particular wavelengths only and nothing else. And as a as far as mathematics go, this energy occupancy is termed as density of states. That is now how many electrons are there per unit energy value. And for an atomic state or a vapor state, this can be approximated easily with a Dirac delta function, which is extremely sharp but intense. Now, this Dirac delta function in our practical purposes are convoluted with broadening coming from the instrument, as well as the fundamental line broadening due to Heisenberg uncertainty principle. Now, electrons are fermions. Because they're fermions, they are not more than 2 electrons are allowed to have the same energy. They value their privacy in a way. So what happens when we form a solid from a gas phase? The atoms come closer and they try to form bonds with each other. But soon the electrons realize that they cannot have the same energy anymore like they had in their atomic state, because they're not allowed to do it by Pauli exclusion principle. So they sort of come to an agreement with each other, and they spread their energies around the atomic energies to form something called bands. The electronic energy bands are energy regions which are allowed or disallowed for an electron to leave. To give an example, I have presented this band structure, electronic band structure of probably the most important material of 20th century, which is silicon. As you can see here now, unlike the atomic spectra, let me show you the atomic spectra once more. There are no discrete regions of allowed energy values. There are now continuous regions of energy values which the electrons can take. There are two parts of these continuous regions. One is called conduction band. And at 0 Kelvin temperature, or absolute zero, everything inside this conduction band is supposed to be filled by electrons. Now, above the conduction band in energy, there is also an allowed region of electronic energies, which is called valence band. But the electrons do not go to the valence band unless they have a perturbation from outside. Now comes a more important observation. Between the valence band and the conduction band, there is a very tiny region which is completely white, not shaded in gray. This tiny region is called an electronic energy gap. This energy gap is observed in insulators or semiconductors. And in typical semiconductors, that electronic energy gap is in the order of visible wavelength or a maximum UV. What does it mean? It means that the electrons can occupy energy values in the conduction band, which is marked in gray. And if they're given enough energies, they can go to valence band as well. But they're not allowed to stay in the middle of these two bands, even if I provide them a little bit of energy to leave. Now it brings us to the interesting discussion about what happens to nanoparticles, for an example. Unlike atomic states, the nanoparticles do not have a density of states which look like Dirac delta function. They also don't have energy states which look like a solid, a typical solid, for an example. For this slide in particular, I have considered a metal. In a metal, the conduction band and valence band, they overlap with each other. And for this reason, we have free electrons which can carry some current when we connect two current leads across a sample. What happens to the nanoparticle is given in the middle. When we reduce the dimension of the particles, every state until the Fermi energy is supposed to be filled with electrons. Because that's a law that's given by statistical mechanics. But right now, because we have a limited size, the number of electrons that take part in filling that band is extremely small. It's much smaller than you'd have if you had a huge chunk of metal. Because these numbers are small, the conduction, either the conduction band or the valence band, can be fully occupied or can be continuous. So they split into small discrete allowed energy levels, which the electrons can occupy. But if they want to go somewhere else, they need a discrete amount, they need a perturbation of a minimum amount of energy that will take them to the next allowed discrete gray line. In the middle diagram, the gray lines indicate where the electrons can live in the energy space, and the white space determines where the electrons cannot stay. What we call formally in the physics community is that the levels have been quantized. And this is why it's called a quantum size effect. Japanese scientist Ryogo Kubo first gave the tools in statistical mechanics to deal with this problem mathematically. And this is why the gap that originates at the Fermi level because of this quantization is named after him, and it's called a Kubo gap. The Kubo gap can be approximated roughly by the expression given in this slide. And what is important to understand here is that if we reduce the dimension of a particle, nanoparticle, let's say, the number of electrons taking part in for filling up these bands also decrease, and they decrease as proportional to the volume. Now, the volume of a sphere is proportional to the d cube or diameter cube of that sphere. So that means if we reduce the particle size, the number of electrons reduce in a cubic manner, inverse cubic manner, let's say. So this gap is also proportional to the inverse cube of the diameter of the particle. There is another way to understand this interesting physical concept. That is by calculating the density of states as a function of the atoms that take part in forming the bands. In the diagram in the left, in the graph in the left, the bottom part gives the density of states of a bulk gold. In the bulk, if you look carefully, this structure is much more smoother than the ones that are on the upper panels. It is because it's formed of many, many, many electrons, and it's a continuous system. When we try to reduce the number of particles that take part in forming this state, let's say if we reduce it to 55 atoms, we see that this density of state structure gets rougher, sharper, and more discretized. Finally, when we reach to 13 atom cluster, let's say, it's no longer a particle, and in physics or chemistry community, these are commonly termed as clusters. The entire space where the electrons used to live before, or the conduction band, has been completely discretized. It is much closer to the atomic picture that we presented in this slide, because they are only allowed to have very discrete energy values. And this kind of electronic behavior, which cannot be explained by classical electrodynamics or classical systems at all, make the nanomaterials interesting, because they do not lie in normal macroscopic systems. They are absolute quantum systems, and their behaviors can only be explained by quantum mechanics alone. Based on the discussion that we had above, there is a way to classify these nanomaterials. Confinement in each direction will discretize the density of states or the energy bands in the corresponding momentum direction of the sample. What does it mean? If we take a sample which is not confined at all, which is given in the bottommost row of the graph, the electronic density of states curve is proportional to e to the power half, and it is a continuous graph. You can see that it's smooth, and there are no sharp or any part of the curve which is annoying. Now, if we reduce the dimension in one particular direction, let's say I deposit an extremely thin film, like let's say graphene for an example, then the smoothness of the curve goes away. And similarly, as we confine it in more and more dimensions, the graphs become smoother and smoother until we reach to the confinement in all three directions. In the second column of the first row, if you notice carefully, for a three-dimensionally confined system, which is also called a nanoparticle or a quantum dot, the theoretical density of states looks exactly like you expect in an isolated atom. But there are more energy levels that are allowed compared to only one or two, which were there in case of an atom. This gives rise to something very interesting in the end. Let's say we take a metal which we know is a good conductor at room temperature as well as low temperature. And then we try to reduce the particle size. What do I mean by when I say that try to reduce the particle size? If we had 1 gram of bulk conducting metal, we will still have 1 gram of bulk conducting metal. But this 1 gram of bulk conducting metal will be made of very, very tiny nanocrystalline parts. So it will not be one single particle or one single big crystal anymore. If we do this, then something which is known as a completely conducting metal or a very good metal can end up behaving like an insulator. In the graph on the right, you can see that when the particle size is about 60 nanometers, then the resistivity is the lowest. okay? And then as we reduce the particle size, the resistivity goes higher and higher. Now, one might argue that it is happening because the material is gathering defects or grain boundary scattering or something like this. But when we reduce the particle size below 11 nanometer or 8 nanometer, the resistivity curve takes a complete upturn at lower temperature, which is happening because of a gap opening at the Fermi surface. This cannot be explained by grain boundary scattering anymore. This is happening because of the gap that we mentioned here. One can understand this concept a little bit by comparing it with a standard theory of p-n junction diode. Because of a gap existing in the junction, we need to provide a bit of higher voltage to get a bit of current. And then the IV characteristics is no longer linear. It becomes a bit like exponential. It is exactly the same thing that's happening in these materials. This feature can give rise to many notorious effects. Let's say you're creating an IC or you're creating a board, and you want to create the smallest possible motherboard that you can imagine by human imagination. But then you are limited by the size of the element of the connectors or the conductors that you use in the circuit. You cannot go below a certain limit because the connectors or conductors itself will no longer remain metallic. They will behave insulating. When we are talking about nanoparticles, there is another very important effect, which is called surface effect. In a sphere, in a rudimentary sphere, the surface to volume ratio varies is proportional to 1 by r. Where r is the radius of the sphere. What does it mean? It means that if we take a larger sphere and a smaller sphere, and if we keep reducing the size, then the surface area of the sphere will slowly become more dominant as we reduce the particle size. And if we reduce it below a certain degree, when r tends to 0, then of course the surface to volume ratio 1 by r will tend to infinity. What it means is that in a small nanoparticles, there are much more number of atoms on the surface of the nanoparticle than you will find in their bulk counterpart, proportional to the atoms sitting inside or volume atoms. Now these atoms that are sitting on the surface, they do not behave exactly the same way as they would have behaved if they're sitting inside, because they are not fully bonded. The atoms that are sitting on the surface, you can see it in the picture, they have much less coordination compared to the atoms that are inside the cluster. Because of this reduction in the coordination, they have free electrons or free bonds, for an example, which are called dangling bonds. So what happens if we have free electrons or free bonds? That means that the electron is looking for another electron to pair up with. It's energetic, it's excited, and it wants to stabilize, or it wants to go down in energy. That makes these nanoparticles chemically much more aggressive than bulk microparticles. And this kind of behavior is routinely used now in catalysis, targeted drug delivery, or anything that has to do with chemical reactions. Because if you use nanoparticles instead of a microparticle, it will react much faster. And in fact, you may not have to use as much material as you had used before. Now, when the surface to volume ratio increases, it doesn't only increase the chemical activity, it increases every surface effect that you can think of. For an example, the surface phonons behave very differently than the volume phonons. And when you reduce the increase the surface to volume ratio by reducing the particle size, the surface phonon effect becomes significant. It also enhances the surface plasmon enhancement, which is primarily responsible for the color of small nanoparticles. We'll discuss about this later in other slides. Now, when you reduce the particle size, there are dangling bonds on the surface, and the systems are more energetic than the others. And this gives rise to also a bit of strain on the system, especially in oxide nanoparticles. When we reduce the particle size, typically we observe that the particles shrink. And what does it mean by particle shrinking? The basic unit cell or the basic element of the particle, the constructive element, that reduces in dimension. Sorry, not in oxides, but in metals. But in oxides, we see the exact opposite trend. The lattice constant increases and the particle sort of expands a bit. However, recently in our lab, we have discovered that if you have a body-centered cubic coordination, like the one that is described here in the top right diagram, the metallic nanoparticles actually expand in size. Now, earlier days, people explained this reduction in particle size in metal nanoclusters by the argument that they want to reduce the surface energy. If they reduce the surface area, they are technically reducing the surface energy, and contraction would be benefited, or contraction would be preferred. But it doesn't explain the observation that we recently had in BCC systems, which is much more complex. And if you look at the graph on the right, the amount of expansion in a BCC cluster is much more than an FCC cluster. However, it still remains an open question till date as to why this happens. When this strain becomes too large, then some systems can also go through a complete phase transition. What do I mean by complete phase transition? Something that was cubic, let's say, will no longer remain cubic. It will completely change and become something else. One of the examples would be size-driven phase transition in iron oxide. Those of you who are interested in going into details, there are very nice literatures about why it happens and what happens after that. However, when it comes to metals, gold, which is supposed to be cubic, that gold that we see every day, it completely changes. It becomes icosahedral, below 5 nanometers of diameter. The argument is again given the same way, that it reduces the surface energy if it has these many facets. Silver also goes through an icosahedral structure when its size is reduced below 5. However, on the BCC metals, like niobium, tantalum, etc., theoretical calculations predict that they should undergo a rhombic dodecahedron. They should become rhombic dodecahedrons. However, until today, experimentally, we have never observed this, and we don't yet know why it doesn't become a rhombic dodecahedron. Maybe in future, someone will be able to produce this or nullify the hypothesis that's there. In our lab, we worked a lot with silver. The silver that we see every day is shining and white in color, as explained in the bottom panel, and it's termed as 3C. The C stands for cubic. In our lab, we were able to grow by electrochemistry a different form of silver. This silver doesn't look white anymore. It looks like pure gold. This silver has extremely low electrical noise. It is much harder and much more brittle than the silver that you find in everyday life. And its electrical resistivity is much higher than bulk silver, normal bulk cubic silver. After doing the X-ray diffraction and careful investigation by transmission electron microscopy, we found that this crystal structure of this new kind of silver is no longer cubic, it is actually hexagonal. By hexagonal, we mean that the lattice constant below and above is completely different. Earlier, the cubic silver had a lattice constant of about 4 angstrom, and now it's completely changed. The symmetry of the system has also changed. Where does nanotechnology come into this, or nanoscience come into this? If we perform a careful ACM of these samples, like displayed in the middle top, we find that this 4H silver, or the new phase of the silver, is actually made of very tiny 20 nanometer sized beads of nanocrystallines. These nanocrystallites help stabilize this otherwise unstable phase of silver. And so far, nobody could stabilize this phase in a bulk macroscopic form. So this tells us also something interesting, that if you reduce the dimension of the size, you can also end up in a different phase. And you might be able to stabilize that phase better than everything else. This material has a lot of opportunities in future to be used in electronics or any other stuff. Now, property of a nanostructure is a very complex thing, and it's an interplay of properties that I described before, like quantum size effect, then surface effect, as well as the lattice distortion due to the strain. In some cases, different interactions can either add up, they can actually help each other to achieve the final property, or they could actually fight with each other, and they can nullify each other in a strange way. So this gives rise to a very complex size dependence that can only be understood by performing careful experiments. Finally, to finish this initial part of the talk, what do we call nanomaterials? What we call nanomaterials depends on the relevant science or physics that we are interested to study. When the property of that particular material significantly deviates from the bulk counterpart, but there is no impurity or no other bad thing in it, then we call it a nanomaterial. For an example, if we are talking about electrical properties of metal nanoclusters, typically the range of interest would be below 10 nanometer of particle size. Ferromagnetic materials like iron or stuff like that, they become super paramagnetic when we reduce their particle size below tens of nanometers, let's ballpark 30 to 40 nanometers, let's say. On the other hand, if someone is interested in looking at quantum confinement in optic systems, like quantum dots and stuff, then the relevant particle size limit would be 5 to 15 nanometers. So there is no direct size limit below which we'll say, yes, this is obviously nanocrystalline, or it's a nanomaterial. No. Because of their different properties which are different from their bulk counterparts, the nanomaterials right now sit in a very interesting place. The nanoscience is one branch which is basically coordinating between physics, chemistry, and biology. For an example, the material that the chemists can prepare in their lab by chemical root synthesis or something like this, or electrochemistry, can be really important or interesting for the physicists to study their magnetism, superconductivity, or any other subject. On the other hand, in order to see what the chemists have grown, the physicists and the engineers come up with instruments like electron microscope that I have discussed before. And that instrument helps the chemists and the biologists also to image fundamental stuff of the human bodies. And the end product that is coming from both physics and chemistry is actually revolutionizing the field of biology every day. Not all of these applications are possible under the scope of this talk. So I have selected 3 specific examples that are a bit different from each other, and I would like to go through them in detail. The first one I would discuss is the optical properties of nanoparticles. I don't know if you're familiar with it, but I think many of you already know. The liquid that is there in the test tubes shown in the middle of the slide are pure gold nanoparticles, which are suspended in either ethanol or water. Now it is very easy to see that the color of these nanoparticles are very different from the color of the gold that Scrooge McDuck, for an example, used to play with. And why does it happen? The answer again comes from the surface effects. In order to understand this, I would like to go a bit detail into what color means in a metal. In a metal, the color of a metal is completely governed by the plasmons. The plasmons are collective oscillation of the conduction electrons in the system that gives rise to a particular response to an incident electromagnetic wave, which in our case happens to be light. In some metals like gold and others, the origin of their color is like interband transition. Now, what happens when we reduce the size? When we reduce the size, the surface phonons become more and more dominant. So if we consider a spherical cube, a spherical metal, for an example, there are two kinds of plasmons that take part into this kind of reaction. One is a volume plasmon that is responsible for the volume conductivity of the system. And then there is surface plasmons, which are a bit different than the volume plasmons, following the argument that I gave before. Now, when you have a bulk or a solid gold bar or something like this, the color is predominantly governed by the volume plasmons. And this is why the color of gold, as you can see in the right-hand side graph, is close to yellow or 600 nanometers in wavelength. As you reduce the particle size, the surface to volume ratio increases, and the contribution of the surface plasmons, they start dominating the contribution of the volume plasmons. And below a certain critical threshold of particle size, the surface plasmons become so dominant, which have, I should rather say, a bit lower energy than the volume plasmons, that the color of the material completely changes. If you reduce the particle size of gold from 150 nanometers to, let's say, 2 nanometers, you can see that the color has a distinct red shift. This red shift is solely dependent on the size of the particle, and this kind of property can also be used to identify the polydispersity or the particle size of the species of interest in the first place. It has found a large range of applications now, for an example, in sensory probes and tumor operations, for an example. It has been quite a few years when people are trying to coat or drive a targeted drug to a tumor, which will also contain these gold nanoparticles. And because their melting point is much lower, and you can trace them by a particular color response, when they reach the tumor, you can shine a bit of laser, and the gold nanoparticle will rapidly melt, along with destroying the tumor entirely. And because of these different types of colors that we can achieve by just changing the particle size, gold nanoparticles are also excellent candidates for surface-enhanced Raman spectroscopy, catalysis, and other stuff, which depend on a particular monochromatic radiation of light. Now that I've talked about metals, let's see what happens in semiconductors. Unlike metals, the color of a semiconductor is governed by the band gap. And the band gap is the thing that I explained before when I described silicon, where the electrons are not allowed to stay. Higher the band gap, the higher energy of incident electromagnetic wave you need for the electrons to mobilize. When we reduce the particle size of a semiconductor, per se, the band edges become much sharper because now the confinement effect is much stronger, and the electrons cannot leave the energy value where they are sitting easily. And this sharper band edge also helps the optical absorption spectra to be much sharper. And not only that, there is a thing in semiconductors called excitons, which are electron-hole bound pairs. The excitonic state is a subband feature which lies in the middle of this energy gap. And in some semiconductors, it's pronounced, and in some semiconductors, it's not. In cadmium selenide, for an example, the example that I have given on the right, the excitonic band is not strong enough if the particle size is 40 nanometers or above. But if we reduce the particle size below 40 nanometers to, let's say, 20 nanometers or so, these excitonic bands will become dominant because now they are more stable, their confinement effect is much stronger, and they move a little bit closer to the conduction band. Because of these reasons, we see a new feature in the optical absorption spectra. So the color of the cadmium selenide, when it is reduced to 20 nanometer, is completely different than the color that it has in 40 nanometer size. Because right now the effective gap of the semiconductor is no longer just what it was before. Now you have a new state to go in, which is an excitonic states. These materials right now are frequently used in making new kinds of waveguides for quantum computers, lasers, photonic crystals, which are going to be used again in quantum computers. Then they're also being used to make something called a metamaterial. The metamaterial is basically the invisibility cloak that we have all been familiar with in Harry Potter movies. And to be honest, the only way to go for that right now is to create photonic crystals of a particular periodicity and size and use some properties of semiconductor quantum dots. It's just like metal nanoparticles, they have also found their application in drug therapy. If you are interested in pursuing this matter any further, I know these two professors in TIFR, which are quite prolific in their research, and they're doing exactly the kind of things that I told you before. Now that I have discussed a bit of physics, hardcore condensed matter physics, I will give an example of an application in soft matter physics, or let's say material engineering, chemical engineering. We all know about the basic properties of hydrophobicity, that if you drop a bit of mercury on glass, the mercury doesn't stick on the glass, but the water sticks and sticks really badly. So this kind of behavior is naturally observed everywhere. And different materials and different liquids have different ways of interaction that govern these materials. However, when we look deeply into nature, it's a bit more complex than that. Let's say if you drop a bit of water on a lotus leaf, the water will immediately go away. It will not stay. But if you drop the same amount of water on a rose petal, for an example, the water doesn't go away. However, the water doesn't spread either. So based on this, there are 9 possible scenarios. I'm not going into the detail of these, but these are the 9 possible scenarios that you can find in nature. Now, using nanotechnology or nano engineering, we are also trying to artificially fabricate these kind of structures in materials that are more industry friendly. Before we go into the details of the experiment, I would like to quickly say how we measure hydrophobicity. There we put a sample in one of these parts of a setup, and then we use a syringe pump. A syringe pump is used to control the flow of water extremely accurately on the surface. Not flow, but the drop of water. Let's say if I want to drop 50 milliliter of water, it will be 50 milliliter, it will not be 100 milliliter or 20 milliliter. And then there is a camera which is facing perpendicular to the interaction space between the water and the sample in question. And that camera is connected to a computer. Now there are two kinds of contact angle measurement. One is called static contact angle measurement, in which we just drop a little bit of water on the surface and we measure the contact angle that it creates. In the figure A on the bottom panel, this theta A is the measure of a contact angle. Now, what is also important is that when you take the water out of the surface, to observe whether this contact angle remains the same or this contact angle changes. For a perfectly hydrophobic sample or super hydrophobic sample with the contact angle above 120 degree, let's say, we expect the water droplet to not stick to the surface at all. And this contact angle should not change when we take out the water. Because if a material is hydrophobic, there is no reason why it would like to keep some water on top of it. It will just let go of it as soon as it's possible. And this is why if you drop a little bit of water on the lotus leaves and you tilt it, the water drops away, goes away. So for a super hydrophobic material, we expect the contact angle to be 120 degree or more, and the difference between the advancing contact angle and the receding contact angle, which is the contact angle when you have almost taken the water out, should be 0. On the other hand, if you have a perfectly hydrophilic surface, like let's say a good metallic surface and water, then the contact angle should be close to 0, and there is no question of receding contact angle because you cannot take the water out anyway. This work was done by one of my senior, Dr. Indrani Chakravarti, who is now a postdoc in Tel Aviv University. She grew nanowires using electrochemistry. Now, by changing the length of the nanowires and the drying conditions, one can end up with different top structures of the whole sample. As you can see, there are 3 different kind of clusters that are formed when the drying conditions are changed. And the size of these clusters, as well as the intercluster separation, governs the hydrophobic properties of these materials. For a particular ratio of the cluster size, as well as the intercluster separation, one can end up exactly like a rose petal scenario. Now it's a bit interesting because if you take, it's a copper nanowire, and if you take plain copper thin film or a plain copper solid, which has been cleaned, chemically cleaned, it's extremely hydrophilic. You drop a little bit of water and the water spreads immediately. It is hydrophilic because this copper surface has free electrons, and that likes to attract water and make bonds with them. On the other hand, the same copper, same metallic copper, when you make these kind of structures, does not allow the water to go in. It behaves like a super hydrophobic material with a contact angle of approximately 160 degree. But on the other hand, if you tilt the sample completely upside down, the water doesn't go away either. So it's a new kind of structure. It's a new kind of system. And this effect is called a rose petal effect, which has not been observed before in a metal surface, so as to say. The reason this happens is that the intercluster separation, that region, the intercluster region, is filled with air in general when it's kept outside. And if the space in this intercluster region is small enough, when you put a little bit of water, this air cannot leave. They are trapped there for an eternity, and they don't allow the water to enter into the spaces between them. This is why the shape of the water droplet is very similar to super hydrophobic shapes, super hydrophobic material. But on the other hand, the tip of the clusters, they're still pure copper and they're still metal, and they still like to stay with the water. So even if you tilt the material upside down, the water does not find any place to go and it sticks to the material. These kind of systems can be used for drug separation. Let's say if you have 2 different kind of toxins or chemicals, one of them is toxic and one of them is not, and the hydrophobic coefficient of one material to the other is vastly different, then if you put a drop of that mixture on the sample and then tilt, you can select one material which will stick to the surface and the other material will not. We extended this study to understand how we can make self-cleaning glasses. This work was done with me and one of my senior, Sriparna Chatterjee, as well, Sriparna Chatterjee in our lab. So we were able to make 2-dimensional nanostrips of copper tetradecanoate by chemical reaction between tetradecanoic acid and copper block. And these 2-dimensional nanostrips were then deep coated. So basically it's very easy to make. You take this kind of a suspension, you shake them very well, you drop them on the glass or whatever material we are interested in. And what we found out, interestingly, was that for a very minimal coverage of the surface area, we can get almost a super hydrophobic contact angle or hydrophobic contact angle. And in that coverage of the surface, that glass still remains optically transparent. That means that we can coat a solar cell panel on the top of a solar cell panel with this kind of materials, which will not block the sunlight to reach. But at the same time, if it rains, it will not let the rain droplets stick on the surface. It will immediately go away. So it also has some kind of chemical applications, and recently this material has found application in clothing, hydrophobic clothing. The third and final example of my talk would be photocatalysis. We all know what catalysts are. They are the things that take part in an experiment, but does not change after the experiment has been done. They are extremely important for everyday things that we do. For an example, in a car, to control the carbon emission, we excuse me. Hello. 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 Am I audible?
Yes, yes.
Okay. Sorry for the interruption. I don't know what happened. Okay. Please hold on a second. Catalysts are very important for everyday use. Like, for an example, they are used routinely in car exhausts to sort of control the carbon emission in the atmosphere. They are also used in factories to separate bad chemicals from the good chemicals. And if I go on talking about the applications of catalysts, it will take a whole day. They're so important. And catalysts have become really dominant in the nano world. The work that I'm going to present now is given by my senior, was done by my senior, Dr. Sriparna Chatterjee, who is a faculty in IMMT Bhubaneswar now. She prepared hydrogen titanate nanotubes and as well as titanium dioxide nanorods in a chemical process called hydrothermal synthesis. So basically, one has to take titanium dioxide, put them in sodium hydroxide, and heat them at different temperatures to reach to different kind of nanostructured shapes. Like at 100 degrees centigrade, you will reach to nanotubes, which have a hollow inside. At about 300 degrees centigrade, you reach nanotapes. Now, what is important to understand is that by changing the shape of these nanostructures, we change the effective surface area or the surface to volume ratio of the system. Now, as explained before, the surface is extremely important when it comes to reactions. Below in this slide, there are two TEM images. One on the left is a nanotube, and you can easily see that there is a difference between the core and the edge because their crystallinity is different. And on the other hand, on the right-hand side, it's a root rod. The way the experiment is done is that we work on a ethylene gas, which is C2H4, and we pass this gas on top of this powder. And we measure how much of C2H4 has reacted or broken down into carbon dioxide. As it turns out, that the nanotubes, hydrogen titanate nanotubes, are the most efficient ones, which gives an efficiency of an industrial level or even above, because it has a very high surface to volume ratio. It is hollow, so the gas literally passes through these small pores and gets either trapped or converts into carbon dioxide. There is a direct correlation between the surface area and the amount of ethylene that has been converted before. These kind of activities can be expanded and into making new kind of catalysts which can be useful in everyday life. I'll finish my talk by talking about the few challenges that we have ahead of us. First of all, we are still behind when it comes to the control of the complex nanostructures that we find by chemical loop synthesis and stuff like that. We need better way to assemble these nanoparticles into the form that we want. For an example, all of you are familiar with carbon nanotubes, and there has been immense discussion about the complex hybrid structures of carbon nanotubes, but we are still many years behind it. The bulk production of the sophisticated nano chips are still very expensive and out of reach for most people, because the efficiency in production of these chips are as low as few percent. Right now, the world record of producing a chip is for IBM technologies, and that's only 13%. So if we look at it this way, we are producing an immense amount of electronic garbage for the future to deal with. We need to have better control for these things. And all of it brings to the fact that optimization in everything that we do right now is very frustrating and time consuming. We need better tools to understand, and that better tools are based on computational algorithms and platforms. When we deal with any solid or any metal or anything in question, we perform something called a first principle calculation. Now, usually we can understand a solid as a collection of atoms and atoms, which are a collection of electrons and ions and stuff. And it's nothing but Schrodinger's equation planned out in three-dimensional lattice. But the number of atoms or the electrons in a solid is so large, which is sort of, let's say, 10 to the power 23, that if we want to understand a solid, we need to solve 10 to the power 23 coupled differential equations. In single crystals or bulk solids, there is a way out because there is a periodic arrangement. And that periodic arrangement helps the problem to reduce down to one differential equation, which is solved using self-consistent method. However, when it comes to nanomaterials or nanoparticles, that doesn't work anymore because we don't have any long-range periodicity. So you are still left with solving, let's say, a few hundreds of differential equations to understand a single simple nanoparticle structure. And right now, there is no way other than that. And it sometimes takes hours and days in most efficient supercomputers we have. So definitely, we need a bit of help in this thing from every community. And for the computational community, of computer science community and everyone, like for an example, people are trying to incorporate neural networks and stuff to make it faster and more easier. And the second problem is that understanding the finite element analysis of a complex nanostructure. When we are talking about simple electric field dependence or stuff of these things, it is that present-day algorithms are still not sufficient to take care of, let's say, an atomically sharp tip, an atomic curvature, or few atom structures. We still find a way around by interpolating from longer to shorter or trying to understand what it could be, and then we find it out experimentally. We really need better algorithms and better handlings for dealing with these things. I would conclude my talk by saying that we need a joint venture between multiple disciplines, including mathematics and computation, to go ahead in the field of nanoscience, to reach it to the potential that lies ahead. For students or anyone who is interested in reading further about this, these are the books that I personally read, and I suggest for others to follow. And now I'm happy to take any question that you have.
Thank you, Dr. Sarkar. It was a very nice presentation. In fact, it was sort of storytelling about the nanoparticles and the different applications of the nanoscience in our real life and the great future that is waiting for us. Thank you once again. Now we move to the question and answer session. The question was asked by Joydeep. In nanochip, it contains of different substance like silicon, copper, aluminum, gold, etc. So how they setting all these components in nano size?
if I understand the question correctly, you want to know how we deal with different kind of metals. Well, to begin with, first of all, it depends on the complexity of the chip. Okay, like for an example, how many layers does the chip have, and stuff like that. Typically, what we make in the labs for research purpose, we coat with one material, we etch it, we create a structure, then we coat it with a resist, and then again etch it after depositing another material. So we don't deposit everything at the one go, and if you have different layers, you need that many number of depositions to do. So it could take days.
The next question from Oniket is, how can we determine required nanomaterials and control them for any
Excuse me, I think I cannot hear you anymore. Hello?
Hello?
I could not hear the question. Sorry, could you please repeat?
The question is from Oniket. How we can determine required nanomaterials and control them for any nanotechnology construction?
Well, first of all, you have to identify the problem that you are dealing with. What exactly do you want to do? Do you want to create an extra hard material? Do you want to create an extremely good conductor? Or, on the other hand, do you want to create an extremely good insulator? Depending on that kind of material, that kind of use, you have to go and do a literature survey or something like, for an example, one moment, I will show you, I will actually show you one website that might be interested, Materials Research Project. I don't know if you are this one. Okay, please hold on for a second. I don't know if I can show it here, but I will try. One moment, please. This is one of the platforms which sort of catalogs all the material properties that has been done on it and what can be done in the future. So my suggestion would be to go here, take a look at the materials that exist already, and then try to understand what suits your purpose. After that, you have to understand, or you have to think, what exactly do you want and why do you want it? For an example, you cannot make a building with nanoparticles of gold, for an example. You have to be careful about what you want. Like, you can use cement mixed with carbon nanotubes, but yes, it all entirely depends on the application that you want to do. And then you have to go and see how you can prepare it. So if you focus the question a bit more, exactly what you want, maybe it's easier to answer.
Thank you, Dr. Sarkar. Now I would like to request our principal sir to say a few words and conclude this session.
Thank you, Dr. Subhrangsu Sarkar, for your illuminating lecture on nanoscience. It's a very lucid presentation. I hope all the participants enjoyed it. Thank you very much. I will also thank for this webinar the coordinator of IQAC of our college, Dr. Chaitari Choudhury, the head of the Department of Computer Science, Sandeepan, and the other two teachers, Shomit and Anupam, for their endeavors. I will congratulate all the students for hearing this lecture, and I thank all my colleagues for being present in this lecture. Thank you very much.
Thank you. Wish you a very nice evening.
Thank you. Thank you.
Thank you. Thank you all the participants for their interest and participation. I would request all the participants to fill the feedback form. The link is given in the chat box. So kindly fill the form and you will receive the e-certificates within 3 days. And once again, thank you, Dr. Subhrangsu Sarkar, for your valuable time and the deep insights and also eliminating the complex mathematical expressions and expressing this like a story to our participants. Thank you. Thank you very much.